Imagine a single point, smaller than the tiniest speck of dust, holding everything that would ever be. Then, in an instant, bang! The universe exploded into existence, a cosmic fireworks show that's still going on. How did we get from that explosive beginning to the complex tapestry of stars, galaxies, and even us? Buckle up, because we're about to take a whirlwind tour through 13.8 billion years of cosmic evolution, from the very first light to the mysteries of today. You'll see how stars are born and die like supernovas, creating the very stuff that makes up your coffee cup and your brain, and discover why this grand cosmic story is more fascinating than any blockbuster movie. The Cosmic Overture. Before the grand symphony of stars and galaxies, there was a moment of pure, unadulterated potential. Imagine a tiny speck, smaller than anything you can conceive, packed with everything that would ever be. It wasn't just hot, it was unimaginably so, a cosmic pressure cooker where even the basic building blocks of reality were just a jumbled mess. Think of it like a chef's pantry before they've even decided what to cook. All the ingredients are there, but they're just waiting. This was the very beginning, a state so dense and energetic that our current understanding of physics starts to get a bit wobbly. Then, something incredible happened: inflation. This wasn't a slow, gentle expansion like a balloon slowly filling with air. It was a ridiculously fast, mind-bogglingly rapid stretching of space itself. In an instant, smaller than the blink of an eye, the universe ballooned out to an enormous size. It's like if you took that tiny speck and, with a cosmic sneeze, turned it into something the size of a solar system, then even bigger, all in a fraction of a second. This explosive growth smoothed out any initial bumps and wrinkles, setting the stage for the more orderly development to come. It's the cosmic equivalent of an entrepreneur getting a massive injection of funding right at the start, allowing them to build a huge company from day one. As this initial burst subsided, the universe began to cool, though cool is a relative term. It was still hot enough to melt anything you can imagine, but now, the fundamental forces that govern everything started to separate. Think of it like water vapor condensing into liquid. The energy was still there, but it began to organize. Particles, like tiny, energetic toddlers, started to form. These weren't the stable atoms we know today, but more like fleeting whispers of matter and antimatter, constantly popping into existence and then annihilating each other. It was a chaotic dance, a cosmic mosh pit of energy and nascent particles, with a slight imbalance tipping the scales in favor of matter. Thankfully for us, otherwise, it would have just been a universe of pure energy, which would make for a rather dull existence. A universe in a teacup. Imagine the entire universe, all of existence, condensed into something as small and familiar as a teacup. This isn't just a whimsical thought experiment, it's a way to grasp the mind-boggling scale of cosmic beginnings. Think about how much information can be held in a tiny seed. The potential for a giant oak tree is all there, just waiting for the right conditions. Similarly, the early universe, incredibly hot and dense, contained the blueprint for everything we see today. At this minuscule stage, the fundamental forces that govern everything, gravity, electromagnetism, and the nuclear forces, might have been unified, like different flavors of ice cream all mixed into one delicious scoop. As the universe expanded and cooled, these forces began to separate, like that ice cream scoop melting and the flavors becoming distinct. This separation allowed for the formation of the building blocks of matter, the tiny particles that would eventually clump together. Consider a speck of dust. It seems insignificant, right? But that speck is made of atoms, which are mostly empty space with a tiny nucleus at the center. The early universe was even more extreme, a state so dense that a single teacup could hold more energy than a billion suns. It was a cosmic pressure cooker, where the very fabric of space and time was being stretched and shaped. This extreme density meant that the laws of physics as we understand them were just starting to emerge, like a toddler learning to walk, a bit wobbly at first. This initial phase, though fleeting, set the stage for everything that followed. It's like the first few brushstrokes on a vast canvas, dictating the entire masterpiece. The subtle variations in density, like tiny ripples on the surface of still water, were the seeds for the galaxies and stars we observe millions of light-years away. Without that incredibly dense, incredibly hot beginning, the vast, starry expanse we know simply wouldn't exist. The Planck epoch swim. Imagine, if you can, a time so infinitesimally brief, it makes a blink of an eye seem like an eternity. This is the Planck epoch, the universe's absolute toddler phase. We're talking about the first 10 to the power of -43 seconds after the Big Bang. Seriously, if you tried to count that fast, you'd still be at zero when the universe was already thinking about forming atoms. It was a time when all four fundamental forces, gravity, electromagnetism, and the two nuclear forces, were all jumbled up, like a toddler's toy box where everything is just one big, chaotic mess. There were no distinct particles, no atoms, not even space and time as we understand them. It was pure, unadulterated potential, a cosmic soup so dense and energetic that our current laws of physics just throw their hands up and say, nope, can't compute. Think of it like this: before a chef starts cooking, all the ingredients are separate. Flour, eggs, sugar. But before that, imagine all those ingredients are somehow fused into one single, amorphous blob. That blob is kind of like the Planck epoch. It's all the stuff of the universe, but not in any recognizable form. It's so hot and dense that matter and energy were practically indistinguishable, like trying to tell the difference between steam and boiling water when it's all just hot. Our understanding of physics breaks down because we're used to things having definite properties, like a solid egg or a liquid batter. In the Planck epoch, everything was a quantum, maybe. This whim of the Planck epoch refers to the incredibly sensitive and unpredictable nature of the universe at this nascent stage. Small fluctuations, tiny variations in energy or density, could have had enormous consequences later on, like a tiny nudge to a Jenga tower that eventually brings the whole thing down. It's like how a butterfly flapping its wings in Brazil might, theoretically, cause a hurricane in Texas. The universe, in its infancy, was incredibly susceptible to these tiny, random events. These initial quantum jitters, these almost imperceptible wiggles, were the seeds of everything that would eventually become galaxies, stars, planets, and even your favorite pizza. The end of the Planck epoch saw the forces begin to separate, like the ingredients in our cooking analogy finally starting to take on their distinct roles. Gravity, being the most independent thinker, likely branched off first. This separation wasn't a gentle parting of ways, it was probably a dramatic, universe-shaking event. As the universe expanded and cooled, these forces went their separate ways, setting the stage for the formation of particles and, eventually, the structured cosmos we observe today. It was the universe's first, wild, and utterly crucial growth spurt, all happening in less time than it takes to sneeze. Inflation's explosive growth. Imagine a moment so brief, it makes a blink of an eye look like an eternity. That's how fast the universe went from being smaller than an atom to something incredibly vast. This wasn't just a little puff, it was an unfathomably rapid expansion, like blowing up a balloon from the size of a speck of dust to the size of a galaxy in less time than it takes for a thought to form. This incredible burst of growth, called cosmic inflation, smoothed out all the wrinkles in the early universe, making it the remarkably uniform place we see today, at least on large scales. Without inflation, the universe might have remained a lumpy, uneven mess, perhaps never even forming stars and galaxies. It's like a cosmic smoothing agent, ironing out all the kinks before the universe even had a chance to get properly dressed. This explosive growth wasn't a gentle unfurling, it was a violent, exponential stretching of spacetime itself. Think of it like a superfast forward button being pressed on reality. In a tiny fraction of a second, the universe stretched by a factor of at least 10^26, meaning it got bigger by a number with 26 zeros after it. To put that in perspective, if you had a single grain of sand and it expanded that much, it would stretch out to be larger than the entire observable universe. This rapid expansion was driven by a mysterious energy field, something we scientists are still trying to fully understand, but its effects are undeniable. It's the ultimate cosmic, get big quick scheme. This period of inflation is crucial because it explains a couple of big puzzles about our universe. For instance, why is the universe so incredibly uniform in temperature in all directions? Before inflation, different parts of the universe were too far apart to have ever talked to each other and reached the same temperature. Inflation, by stretching things out so dramatically, brought regions that were once close together into contact, allowing them to equalize their temperature. Then, it pushed them apart again at an astonishing speed, leaving them with the same temperature but now vastly separated. It's like everyone in a small, cozy room agreeing on the perfect thermostat setting, and then the room suddenly expands to the size of a continent, but everyone remembers that perfect temperature. Furthermore, inflation helps explain why the universe appears so flat, geometrically speaking. If you look at a very small section of a curved surface, like a tiny patch on a basketball, it looks flat. Inflation stretched the universe so much that any initial curvature was ironed out, making it appear remarkably flat on the scales we can observe today. It's as if the universe started with a slight wobble, but inflation blew it up so much that the wobble became imperceptible, leaving us with a smooth, flat expanse. This incredible, fleeting moment of hyperexpansion laid the groundwork for everything we see, from the smallest subatomic particles to the grandest cosmic structures. The quark-gluon plasma ballet. Imagine the universe just after the Big Bang, not as a quiet emptiness, but as a roiling, incredibly hot soup. This wasn't just any soup, it was a primal brew where the very building blocks of matter, quarks and gluons, were not yet confined into protons and neutrons. Think of it like a mosh pit at a rock concert, but instead of sweaty teenagers, you have these superenergetic fundamental particles, zipping around at near light speed. They were so hot and dense, about 100 times hotter than the sun's core, that they couldn't hold onto each other in the way they do now. Quarks, which are like the Lego bricks of matter, and gluons, the glue that holds them together, were all individually splashing around in this cosmic cauldron. This chaotic, superhot state is what scientists call quark-gluon plasma. It's a fluid, but not like water or honey. It's a perfect fluid, meaning it flows with almost no resistance, a bit like trying to stir molasses in January versus stirring a light vinaigrette. This incredibly low viscosity is one of its most surprising characteristics. For a long time, physicists thought this early universe soup would behave more like a gas, with particles bouncing around independently. But experiments, particularly at places like the Large Hadron Collider, have shown it's more like a liquid, a cosmic ballet of these fundamental particles swirling and interacting in complex ways. The ballet isn't choreographed in the human sense, of course. It's a dance governed by the fundamental forces of nature. When these quarks and gluons collide and interact, they create ripples and waves within the plasma, much like dropping a pebble into a pond. These collective behaviors are what make it a perfect fluid. Physicists study these patterns, looking at how the plasma bends or flows around disturbances. It's like watching a tiny, incredibly energetic whirlpool form and dissipate in super slow motion, revealing the underlying rules of the universe at its most fundamental level. This phase of the universe, though fleeting, laid the groundwork for everything that followed, shaping the very fabric of the cosmos we see today. Baryogenesis, the matter-antimatter mystery. In the universe's infancy, a cosmic game of creation and annihilation was playing out, and we're still trying to figure out the rules. Picture this, right after the Big Bang, the universe was a scorching hot soup, brimming with particles and their equally nasty twins, antiparticles. For every electron, there was a positron, for every proton, an antiproton. They were like mirror images, identical in mass but opposite in charge. When a particle and its antiparticle met, poof, they'd annihilate each other in a burst of pure energy. It was a universe teetering on the brink of disappearing into nothingness, a cosmic dance of mutual destruction. Now, here's the baffling part. If matter and antimatter were created in equal amounts, as our best theories suggest, they should have completely wiped each other out. The universe should be a vast, empty expanse, filled only with light. But that's clearly not the case. We're here, reading this, made of stuff. Planets, stars, galaxies, all this solid, tangible matter exists. This implies that at some point, a tiny imbalance must have occurred. A microscopic preference for matter over antimatter, a cosmic nudge in the right direction, allowed a sliver of matter to survive the great annihilation. Scientists call this crucial moment baryogenesis. It's the process that supposedly tipped the scales, creating the slight excess of matter that forms everything we see. Think of it like a baker making a batch of cookies, but accidentally adding just one extra grain of flour. That tiny, almost imperceptible difference makes all the difference in the final product. In the early universe, this slight asymmetry meant that for every billion antimatter particles, there were 1,000,001 matter particles. That one extra particle per billion is all it took for matter to win the cosmic lottery. The mystery, however, is how this imbalance happened. The standard model of particle physics, our current best description of fundamental particles and forces, predicts a certain amount of asymmetry, but it's nowhere near enough to explain the universe we observe. It's like finding out your cookie recipe is missing a crucial ingredient, or that the ingredient you did use isn't quite right. Physicists are exploring various theories, from new particles and forces to subtle differences in how matter and antimatter behave under extreme conditions, hoping to solve this fundamental puzzle of why we exist and antimatter seems to be mostly gone. The Great Annihilation. The universe, in its nascent stages, was a chaotic ballet of matter and antimatter. Imagine two identical twins, one good and one evil, locked in an eternal dance. For every particle of normal stuff, like the atoms that make up you and me, there was a corresponding antiparticle. Think of it like a cosmic mirror image. When these twins met, they didn't just hug, they annihilated each other in a burst of pure energy. This wasn't a polite disagreement, it was a full-on, no-holds-barred cosmic explosion. This energetic showdown, known as the Great Annihilation, was incredibly efficient. Every time a particle and its antiparticle bumped into each other, they vanished, transforming into light. It was like a bar fight where everyone involved suddenly turned into a laser beam. This process happened billions upon billions of times in the early universe. If matter and antimatter had been created in perfectly equal amounts, the universe today would be a very different, and much emptier, place. It would likely be just a vast expanse of radiation, with no stars, no planets, and certainly no one to ponder its existence. So, why aren't we all just pure energy now? Well, it turns out there was a slight imbalance, a tiny cosmic hiccup. For every billion antiparticles, there was just one extra particle of normal matter. This minuscule surplus is the reason we exist. It's like having a massive pile of dominoes ready to fall, but just one tiny pebble preventing the entire structure from collapsing. This one extra particle, and its friends, were the lucky survivors, the ones who got to stick around and form everything we see. This slight asymmetry is one of the biggest mysteries in physics. Scientists are still trying to figure out precisely why this imbalance occurred. Was it a random cosmic fluke? Or was there some underlying principle that favored matter over antimatter? It's a question that keeps cosmologists up at night, pondering the secrets of the universe's infancy. Without that tiny nudge, that almost imperceptible preference for matter, the universe as we know it simply wouldn't be. It's a stark reminder that even the smallest differences can have monumental consequences on the grandest scale. The photon epoch's light show. The universe was a blazing inferno, a cosmic soup of pure energy where light particles, or photons, ruled supreme. Think of it like a gigantic, super-hot lava lamp, but instead of wax blobs, it was filled with incredibly energetic light. These photons were zipping around at the speed of light, bumping into everything and creating a dazzling, chaotic light show that lasted for what felt like an eternity. It wasn't just any light, though, it was so intense that it was constantly creating and destroying matter in a frenzied dance. Imagine a toddler with a box of crayons, scribbling wildly across a giant canvas. That was the early universe, a riot of energy and fleeting particles. This period, known as the photon epoch, was characterized by an incredibly dense and hot plasma. It was too hot for even atoms to form, let alone anything more complex. Photons were the main characters, constantly interacting with charged particles like electrons. This interaction meant that light couldn't travel very far without being absorbed or scattered, much like trying to see through a thick fog. If you tried to shine a flashlight in this primordial soup, the beam would just disappear after a few millimeters. The universe was opaque, a blinding white light everywhere you looked, with no stars or galaxies to break up the monotony. As this fiery epoch continued, the universe was also expanding and cooling, albeit very slowly at first. This cooling was crucial because it meant that eventually, the energy levels would drop enough for something remarkable to happen. It was like a massive pot of boiling water slowly coming down to a simmer. The photons, which were the stars of the show, began to lose some of their punch. Their incredible energy started to wane, and with that, the universe's chaotic creation and destruction of matter began to calm down. The stage was being set for a new act, one where light would finally be able to travel freely. Nucleosynthesis, forging the first elements. Imagine the universe as a cosmic kitchen, and in the very beginning, it was mostly just hydrogen and helium soup. Not a lot of variety, right? It was like a restaurant that only served plain toast. But then, things got hot. Really, really hot. As the universe cooled down a tiny bit after the Big Bang, it wasn't quite hot enough for atoms to hold onto their electrons, so they were just bare protons and neutrons, the basic building blocks of matter. Think of them as lonely Lego bricks floating around. Then, as the universe continued its grand cooling process, these lonely Lego bricks started bumping into each other. When a proton and a neutron got too close, they decided to stick together, forming the nucleus of a deuterium atom, which is basically a heavier version of hydrogen. It was like two of those Lego bricks snapping together. This process, called nucleosynthesis, was the universe's first attempt at cooking up something more interesting than just plain hydrogen. It was a bit like a toddler discovering they can stack two blocks. As the universe kept cooling, the temperature dropped just enough to allow these newly formed deuterium nuclei to collide with other protons and neutrons. Sometimes, a deuterium nucleus would grab another proton, creating helium-3, another hydrogen cousin. Other times, it would snag a neutron, forming helium-4, the helium we know and love, or at least recognize from balloons. This was the universe's first real culinary success, producing the two most abundant elements after hydrogen, helium and a tiny smidgen of lithium. It was like the toddler went from stacking 2 blocks to building a small, wobbly tower. For a brief period, maybe the first few minutes, the universe was a furnace, churning out these simple elements. After this initial burst of creation, the universe expanded and cooled too much for these nuclear reactions to continue. It was like the kitchen closed for the night, and the cosmic chefs packed up their tools. So, for billions of years, the universe was mostly stuck with hydrogen and helium, with only trace amounts of lithium. All the heavier elements, like the carbon in your body, the oxygen you breathe, and the iron in your blood, had to wait for a much later, and much more dramatic, event, the birth and death of stars. Those stars became the next, much more sophisticated, cosmic kitchens. The Dark Ages dawn. The universe, having just emerged from its fiery infancy, plunged into a period so dark and uneventful, it's been aptly nicknamed the Cosmic Dark Ages. Imagine a vast, empty room after a spectacular fireworks show, the echoes fade, the smoke clears, and for a while, it's just dim. That's kind of what happened. After the Big Bang's initial flash and the subsequent formation of the first, simple atoms like hydrogen and helium, the universe was a pretty uniform, albeit cooling, soup. There were no stars, no galaxies, just diffuse gas spread out over an immense expanse. It was a quiet time, a cosmic lull before the grand symphony of stellar creation began. This era, lasting for hundreds of millions of years, was characterized by the absence of light-emitting objects. Think of it as the universe taking a deep breath. The only light present was the fading afterglow of the Big Bang itself, the cosmic microwave background radiation, which had stretched and cooled so much that it was no longer visible light but rather microwaves, like the ones your kitchen appliance uses. This gas wasn't entirely still, though. Tiny, almost imperceptible quantum fluctuations from the earliest moments of the universe began to pull matter together ever so slowly, like a gentle breeze nudging dust bunnies into slightly larger clumps. Gravity, the universe's ultimate matchmaker, was hard at work during these dark times. It was patiently gathering the hydrogen and helium gas into increasingly dense pockets. These weren't galaxies yet, more like cosmic nurseries waiting for their spark. Eventually, these gas clouds became so massive and dense that their cores reached a critical temperature and pressure. This was the trigger. The atoms within these cores began to fuse, initiating nuclear reactions and, at long last, igniting the very first stars. These pioneering stars were giants, much larger and brighter than our own sun, burning through their fuel rapidly and spewing out heavier elements forged in their fiery hearts. This was the end of the Dark Ages and the dawn of the reionization era, where the light from these first stars began to push back the cosmic darkness. Recombination's gentle release. The universe, once a fiery, opaque soup of charged particles, began to cool. Think of it like a pot of boiling water that's slowly being taken off the heat. As the temperature dropped, something remarkable happened. Electrons, those zippy little negative charges, finally decided to settle down and get cozy with the positively charged protons. This wasn't a violent smash-up, it was more like a gentle, cosmic embrace. This settling down is called recombination. Before this, light couldn't travel far because it kept bumping into all those free-floating charged particles, like trying to drive through a thick fog. But once the electrons got captured by protons, forming neutral atoms, the fog lifted. Suddenly, light could zip around freely. This moment is often called the surface of last scattering because it's the last time light interacted with matter before traveling unimpeded across the cosmos. It's as if the universe suddenly became transparent, and we're still seeing the echoes of that initial light show. Imagine a crowded dance floor where everyone is bumping into each other, making it impossible to see across the room. Then, suddenly, everyone finds a partner and settles down. Now, you can see all the way to the other side of the dance floor. That's essentially what happened with the universe. This release of light, now able to travel unimpeded, is crucial because it's the oldest light we can possibly detect, the cosmic microwave background radiation. It's a snapshot of the universe when it was only about 380 years old, a baby picture of the cosmos. This freed light carried information about the conditions of the early universe, like a message in a bottle cast into the cosmic ocean. Scientists study this ancient light, looking for subtle patterns and variations, to understand how the universe evolved from that relatively smooth, early state into the vast, complex structure of galaxies and stars we see today. It's a bit like finding an old, faded photograph and trying to decipher the details to learn about the past. The cosmic microwave backgrounds whisper. Picture the universe as a giant, dark room. For billions of years, it was mostly empty and quiet. Then, about 380 years after the Big Bang, something amazing happened. The universe cooled down enough for tiny particles, like electrons and protons, to finally hold hands and form atoms. This was a big deal because before this, the universe was like a superhot, foggy soup where light couldn't travel freely. Think of it like trying to see through a thick fog. Light just bounces around everywhere. When atoms formed, the fog cleared. Suddenly, light was set free to zip around the cosmos. This first light is still traveling today, and it's what we call the cosmic microwave background, CMB. It's like a faint echo of the universe's baby pictures, a snapshot of what everything looked like when it was incredibly young. This light has been stretched out over billions of years, so instead of being visible light, it's now in the form of microwaves, which are like invisible radio waves. It's a whisper from the dawn of time, so quiet you'd need special ears to hear it. Scientists use supersensitive telescopes, like the Planck satellite or the WMAP probe, to listen to this whisper. They found that this microwave background isn't perfectly smooth, it has tiny temperature variations, like faint ripples on a calm pond. These little hot and cold spots are incredibly important. They are the seeds from which all the galaxies and stars we see today eventually grew. Imagine throwing a handful of sand into water. The initial splash creates ripples that eventually lead to the formation of larger patterns. Those tiny temperature differences in the CMB are the cosmic equivalent of that initial splash. These subtle variations, no more than a few parts in 100, tell us so much about the early universe. They reveal the ingredients of the cosmos, how much normal matter, and dark energy there was. It's like finding a recipe card from the universe's first kitchen, detailing exactly what went into making everything. Without this ancient light, understanding the universe's evolution would be like trying to solve a puzzle with most of the pieces missing. The CMB is our most direct link to the universe's infancy, a cosmic lullaby that has been playing for nearly 13.8 billion years. The first stars ignite. The universe, once a dark and empty expanse, began to stir. Imagine a cosmic nursery, vast beyond comprehension, filled with the most basic ingredients, hydrogen and helium. These weren't the elements we know today, like the oxygen we breathe or the iron in our blood. These were the building blocks, the primordial soup. For eons, gravity, that unseen force that keeps our feet on the ground, was patiently at work. It tugged and pulled at these simple gases, drawing them closer and closer. Think of it like a giant, invisible hand slowly gathering wisps of smoke into denser and denser clouds. These clouds grew, becoming massive, colossal structures, so large they dwarf anything we can picture. As these gas clouds collapsed under their own immense weight, the pressure and temperature at their cores began to skyrocket. It was like squeezing a balloon tighter and tighter, the air inside gets warmer. Eventually, the conditions became so extreme, so unbelievably hot and dense, that something truly magical happened. The hydrogen atoms, under this incredible pressure, began to fuse together. This fusion process, a kind of cosmic alchemy, released an enormous amount of energy. It was the universe's first light show, a spectacular burst of radiance that pierced the ancient darkness. These were the very first stars, born from the collapse of unimaginably large clouds of gas. These early stars were giants, far larger and hotter than our sun. They were also incredibly short-lived, burning through their fuel at a furious pace. Picture a bonfire that's fed with a huge pile of wood. It blazes brilliantly but is gone much quicker than a small, smoldering ember. These massive stars lived fast and died young, completing their life cycles in mere millions of years, a blink of an eye in cosmic terms. When they finally met their explosive end, in cataclysmic events called supernovae, they scattered heavier elements, forged in their fiery cores, into the surrounding space. This was crucial, as these heavier elements would later become the building blocks for planets, and eventually, for life itself. Without these first explosive deaths, the universe might have remained a sterile place, forever filled with only the simplest gases. Population third stars, the universe's first architects. These were the universe's very first stars, born from a cosmic stew of only hydrogen and helium, the simplest elements created in the Big Bang's fiery aftermath. Think of them as the universe's primordial builders, tasked with forging the very materials needed for everything that came later. Unlike today's stars, which have a smorgasbord of heavier elements like carbon and oxygen to help them form, these early giants had practically nothing to work with. It's like trying to bake a cake with only flour and water, no sugar, no eggs, no chocolate chips. These population third stars were absolute behemoths, hundreds of times more massive than our sun. Imagine a star so big it would make our sun look like a tiny speck of dust. This enormous size meant they burned incredibly hot and bright, living fast and dying young. Their lives were fleeting, lasting only a few million years, a blink of an eye in cosmic terms. They were the rock stars of the early universe, leaving a dramatic exit. Their death was spectacular. When these massive stars ran out of fuel, they exploded as supernovas, but not just any supernovas. These were the universe's first nucleosynthesis events, forging heavier elements in their explosive deaths. It was in these fiery finales that elements like carbon, oxygen, and iron, the building blocks of planets and life as we know it, were first created and scattered across the cosmos. Without these stellar fireworks, the universe would have remained a much simpler, less interesting place, devoid of the complexity we see today. The remnants of these explosions seeded the next generation of stars and galaxies. It's a bit like a chef using the scraps from one meal to prepare the ingredients for the next. These newly forged elements became the raw materials for population second stars, which then went on to create even more diverse elements. This process of stellar birth, death, and rebirth is the grand cosmic recycling program that has continuously enriched the universe, paving the way for everything from rocky planets to, well, us. Galaxies begin to gather. The vast, empty stretches of the early cosmos began to shrink as gravity, that invisible cosmic puppeteer, started its work. Imagine a giant, invisible tug-of-war, with matter on one side and the universe's relentless expansion on the other. For a while, expansion seemed to be winning, stretching everything thinner. But then, clumps of dark matter, like tiny invisible marbles, started to attract more and more regular matter, the stuff that makes stars and planets. These clumps grew, like a snowball rolling down a hill, gathering more and more material. These growing clumps weren't just random piles, they were the seeds of galaxies. Think of them as cosmic nurseries, where the ingredients for star formation were being concentrated. The more matter that gathered, the stronger the gravitational pull became, drawing in even more gas and dust from the surrounding darkness. This process wasn't instantaneous, it took millions, even billions, of years. It was a slow dance of attraction, a cosmic ballet choreographed by gravity. As these proto-galaxies grew, they started to bump into each other. It wasn't a violent crash in the way we might imagine a car accident. Instead, it was more like a slow, gravitational embrace. Galaxies would merge, their stars and gas swirling together, sometimes creating spectacular bursts of star formation. It's like two clouds of smoke slowly merging, their individual identities blending into a larger, more complex form. These mergers were crucial, helping to build the massive galaxies we see today, from the majestic spirals to the more chaotic, irregular shapes. This cosmic gathering was how the universe began to fill with the grand structures that would eventually host planets, moons, and perhaps, life. The first black holes emerge. The universe, still a cosmic infant, was a very different place. Imagine a dark, vast ocean, but instead of water, it was filled with a primordial soup of hydrogen and helium gas, with a smattering of dark matter. Gravity, that relentless cosmic sculptor, was already at work, pulling these gas clouds together. These weren't gentle cuddles, these were massive, inexorable squeezes. As these gas clouds grew denser and denser, the pressure and temperature at their centers skyrocketed. Think of it like trying to stuff an entire galaxy's worth of stuffing into a tiny pillowcase. Eventually, some of these collapsing gas clouds became so massive and so hot that they ignited, not with a gentle spark, but with a furious inferno. These were the very first stars, giants born from the raw materials of the Big Bang. They were enormous, hundreds of times more massive than our sun, and they burned incredibly hot and bright, but their lives were fleeting, like a spectacular fireworks display. These early stars were the universe's first heavy-duty recycling plants. Their immense gravity and insatiable nuclear furnaces fused lighter elements like hydrogen and helium into heavier ones, like carbon and oxygen. When these colossal stars reached the end of their short, dramatic lives, they didn't just fade away. Oh no, they went out with a bang, a supernova explosion that scattered these newly forged heavier elements across the cosmos. This enriched the cosmic gas clouds, providing the building blocks for future generations of stars and, eventually, planets. But among these stellar giants, something even more mysterious and powerful was beginning to form. As the universe aged, pockets of incredibly dense matter began to collapse under their own immense gravity. These weren't stars in the making, these were regions where gravity was so overwhelming that nothing, not even light, could escape its clutches. These were the first black holes. They formed from the remnants of the most massive stars that, after their explosive supernova deaths, collapsed inward without any outward force strong enough to stop the implosion. Picture a cosmic drain, sucking in everything around it. These primordial black holes were the universe's ultimate vacuum cleaners, growing by devouring surrounding gas and dust, and even occasionally swallowing nearby stars whole. These early black holes, though perhaps smaller than the supermassive ones we see at the centers of galaxies today, were crucial in shaping the early universe. Their immense gravitational pull could influence the formation of galaxies, acting as anchors around which gas and dust could gather, kickstarting the process of galaxy formation. They were the silent, invisible engines of cosmic evolution, their presence marked only by the swirling matter they consumed and the light that could never escape their event horizons. They were the universe's first true enigmas, born from the extreme conditions of its infancy. Dark matter's invisible hand. Imagine the universe as a cosmic dance floor. We, with all the stars, galaxies, and planets we can see, are the brightly lit dancers, twirling and leaping. But there's a whole lot more going on in the shadows, a mysterious presence guiding the steps of those visible dancers. This unseen force is dark matter, and it's like the invisible choreographer of the cosmos. It doesn't shine, it doesn't reflect light, so we can't see it directly. It's the ultimate wallflower, but one with an incredible amount of influence. Scientists first suspected this cosmic wallflower's existence when they noticed galaxies spinning much faster than they should. Think of a merry-go-round. The faster it spins, the more likely you are to be flung off. Galaxies are held together by gravity, the same force that keeps your feet on the ground. But the visible stuff in galaxies just wasn't enough to provide the gravitational pull needed to keep them from flying apart at their observed speeds. It's like seeing a merry-go-round spinning at breakneck speed with only a few kids on it. You'd expect them to be airborne, yet they're perfectly safe. Something else must be providing extra grip. This extra grip comes from dark matter. It's estimated to make up about 85% of all the matter in the universe. That means for every single star or planet you can point to, there are roughly 5 times more invisible dark matter particles holding things together. It's not just about galaxies, dark matter also played a crucial role in the early universe. Its gravitational pull acted like cosmic scaffolding, attracting normal matter and allowing the first stars and galaxies to form. Without dark matter's subtle, unseen influence, the universe might have remained a diffuse, uninteresting haze, never assembling into the magnificent structures we observe today. It's the silent architect, shaping the grand designs of the cosmos. The cosmic web's grand design. Imagine the universe as a giant, invisible spiderweb, but instead of flies, it catches galaxies. This isn't just a pretty picture, it's the cosmic web, a colossal structure made of dark matter and gas, with galaxies clustered along its threads. It's like the universe decided to knit itself a giant, lacy sweater. These threads, called filaments, stretch for millions of light years, connecting vast pockets of matter. Think of it like a superhighway system, but for galaxies, guiding them on their cosmic journeys. These filaments aren't just random strings, they converge at massive knots, called clusters, where the biggest and brightest galaxies tend to hang out. It's the universe's version of a bustling metropolis, packed with celestial neighbors. The spaces between these filaments are vast, almost empty voids, like the quiet suburbs of our cosmic city. This grand design emerged from tiny fluctuations in the early universe, amplified by gravity over billions of years. It's a testament to how simple rules can create incredibly complex structures, much like how a few basic ingredients can bake a magnificent cake. The cosmic web isn't static, it's constantly evolving. Galaxies are pulled along these filaments, merging and interacting, shaping the web itself. It's a dynamic, ever-changing tapestry, with new stars forming and old ones dying, all happening within this immense network. Even the seemingly empty voids aren't entirely empty, they contain a diffuse sprinkle of gas and a few straggler galaxies. This intricate structure, so vast it's almost beyond comprehension, is the scaffolding upon which the universe's story is written. Reionization, lighting up the cosmos. The universe, once a murky, neutral fog, began to clear. Imagine a room filled with a dense, smoky haze, so thick you can barely see your hand in front of your face. That was the early universe after the Big Bang. After cooling down, the abundant hydrogen and helium atoms had captured their electrons, forming neutral gas. This neutral gas was a formidable obstacle to light, like a cosmic curtain. Then, something amazing happened. Around 400 million years after the Big Bang, the first stars and galaxies ignited, and their powerful ultraviolet light began to break apart these neutral atoms. This process, known as reionization, was like a cosmic dawn. Those first stellar furnaces were incredibly hot and bright, spewing out photons with enough energy to strip electrons away from protons, turning neutral hydrogen back into its ionized state. Think of it like a giant, universe-wide switch being flipped, gradually turning on the lights. These early galaxies, though small and scattered, were the trailblazers, each one a tiny beacon in the darkness. The universe wasn't suddenly flooded with light, it was a gradual, patchy process, with pockets of ionized gas expanding outwards like bubbles in boiling water. The ultraviolet light from these nascent galaxies acted like cosmic scissors, snipping the bonds between electrons and protons. This reionization campaign lasted for hundreds of millions of years, a critical phase where the universe transitioned from a dark, opaque medium to the transparent cosmos we observe today. It's a bit like a forest fire, where patches of dry undergrowth burn away, leaving behind clearings. These clearings of ionized gas allowed light to travel much farther, paving the way for the formation of larger structures and eventually, the complex universe filled with galaxies, stars, and planets that we inhabit. Without reionization, the universe would still be a dim, hazy place, and we wouldn't be here to ponder its mysteries. Galaxy evolution, a cosmic dance. Galaxies, those immense islands of stars, gas, and dust, are not static entities. They are born, they grow, and they change over cosmic time scales, a grand ballet choreographed by gravity. Imagine a bustling city that starts as a few scattered buildings and gradually expands, adding skyscrapers, neighborhoods, and intricate road networks. Galaxies undergo a similar, albeit much grander, process. Initially, they might be small, irregular collections of matter, like a fledgling village. Over billions of years, they attract more material, merging with their neighbors and accumulating more stars and gas. This cosmic dance is often a violent affair, with galaxies colliding and merging, reshaping each other in spectacular displays of stellar fireworks. These mergers are crucial for galaxy growth, akin to cities annexing surrounding towns to become metropolises. The type of galaxy a celestial body becomes is heavily influenced by its history of mergers and its environment. Spiral galaxies, like our own Milky Way, with their elegant arms, often form in less crowded regions where they can grow more gradually. They are like well-established suburbs, expanding outwards with a structured, yet dynamic, growth. Elliptical galaxies, on the other hand, are typically more spherical or football-shaped and are often found in the dense centers of galaxy clusters. These giants are thought to be the result of numerous chaotic mergers, where smaller galaxies have been gobbled up over time, much like a large corporation acquiring many smaller businesses, leading to a more consolidated and less structured form. The gas within these galaxies also plays a vital role, acting as the fuel for new star formation. When galaxies collide, this gas can be compressed, triggering bursts of star birth, or it can be stripped away, starving future star production. The evolution of galaxies is not just about their shape and size, it's also about the chemical enrichment of the universe. As stars are born, live, and die, they forge heavier elements in their cores and then disperse them into space through stellar winds and supernova explosions. These newly forged elements, like carbon, oxygen, and iron, are then incorporated into the next generation of stars and planetary systems. So, each new galaxy is born with a slightly different chemical makeup than its predecessors, a cosmic inheritance that influences the potential for life. It's like bakers using ingredients from previous batches of bread to create new recipes. The fundamental elements are there, but the proportions and types of additives change over time, leading to a richer variety of outcomes. This ongoing process means that galaxies are not just evolving in structure but are also becoming more chemically complex, paving the way for more intricate cosmic structures. Star formation cycles. Stars aren't born and then just sit around like grumpy old men. They go through a whole life cycle, a cosmic drama of birth, life, and eventual, sometimes spectacular, death. Think of it like a cosmic recycling program. Imagine a giant cloud of gas and dust, mostly hydrogen and helium. This isn't just any old cloud, it's a stellar nursery. Gravity, that persistent force that keeps your feet on the ground, and unfortunately, your spare tire on your waist, starts to pull this gas and dust together. As more material clumps up, the center gets denser and hotter. Eventually, it gets so hot and so dense that nuclear fusion ignites. Boom. A star is born. It's like a cosmic oven turning on, fusing hydrogen atoms into helium and releasing an incredible amount of energy. This is the main sequence phase, where stars spend most of their lives, happily churning out light and heat. Our own sun is currently in this phase, living its best stellar life. But even stars can't live forever. When a star runs out of hydrogen fuel in its core, things get interesting. For stars like our sun, they start to swell up, becoming red giants. Imagine a balloon that's been overinflated, looking much bigger and redder than before. During this phase, they fuse helium into heavier elements like carbon and oxygen. It's a bit like a baker trying a new recipe, experimenting with different ingredients. Eventually, the outer layers of these stars drift away, creating beautiful, glowing clouds called planetary nebulae. Don't let the name fool you, planets have nothing to do with it. It's just that early astronomers thought they looked like planets through their telescopes. What's left behind is a dense, hot core called a white dwarf, which slowly cools down over billions of years, eventually becoming a cold, dark black dwarf. It's the ultimate cosmic retirement plan. Now, for the really big stars, the show doesn't end with a gentle fade-out. These massive stars have a much more dramatic exit. After exhausting their hydrogen fuel, they go through a series of fusion stages, creating heavier and heavier elements like iron. But iron is a dead end for fusion, it actually takes energy to fuse iron, rather than releasing it. This causes the core to collapse catastrophically. The star then rebounds in a colossal explosion known as a supernova. Think of a firework display on steroids, but on a cosmic scale. These explosions are so powerful they can outshine entire galaxies for a brief period. Supernovae are incredibly important because they forge elements heavier than iron, like gold, silver, and even the calcium in your bones. So, the next time you admire a piece of jewelry or bite into a steak, remember that those atoms might have been created in the fiery heart of a dying star. What happens after the supernova depends on the initial mass of the star. If the remaining core is not too massive, it can become a neutron star. These are incredibly dense objects, packing the mass of a sun or two into a sphere only about 20 kilometers across. Imagine squeezing Mount Everest into a sugar cube, and you're getting close to the density. If the core is even more massive, gravity wins completely, and it collapses into a black hole, an object with gravity so strong that nothing, not even light, can escape. These stellar remnants, whether they are cooling white dwarfs, spinning neutron stars, or enigmatic black holes, are the final act in the star's life, and they often play a crucial role in seeding the next generation of stars and planets. It's a continuous cycle of cosmic creation and destruction, a never-ending story written in the language of gravity and fusion. Supernovae, stellar endings, cosmic beginnings. The explosive death of a star, a supernova, is one of the most cataclysmic events in the cosmos. It's not just a dramatic finale, it's a crucial act of cosmic recycling. Think of it like a baker throwing out burnt cookies. Not only does it get rid of the bad, but the crumbs can be used to make something new and delicious. These stellar explosions are responsible for scattering heavy elements, forged in the star's core over millions or billions of years, out into the vastness of space. Without these cosmic fireworks, the universe would be a much simpler, and frankly, duller place, lacking the building blocks for planets and life as we know it. When a massive star, many times heavier than our sun, runs out of fuel, it can no longer support its own immense weight. Gravity takes over with a vengeance, crushing the star's core inward at incredible speeds. This implosion triggers a rebound, a shock wave that blasts outward, tearing the star apart in a spectacular display of light and energy. It's like a giant cosmic pressure cooker that finally explodes. For a brief period, a single supernova can outshine an entire galaxy, a truly mind-boggling amount of light. Even smaller stars, like our sun, can meet a fiery end, though in a less explosive fashion, but it's the massive stars that truly put on the grandest show. These explosions are not just pretty light shows, they are elemental factories. Inside stars, lighter elements are fused together to create heavier ones. For instance, carbon and oxygen are made this way. but elements like iron, gold, and uranium. These can only be forged in the extreme conditions of a supernova. When the star explodes, these newly created heavy elements are flung far and wide. They mingle with existing gas and dust clouds, enriching them. Eventually, these enriched clouds can collapse under their own gravity, forming new stars and planetary systems. So, the iron in your blood, the calcium in your bones, even the gold in your jewelry, all likely originated in the heart of a long-dead star. It's a cosmic inheritance, passed down through generations of stellar explosions. The remnants of a supernova are just as fascinating as the explosion itself. What's left behind can be a rapidly expanding cloud of gas and dust, called a nebula, which might look like a beautiful cosmic watercolor painting. Or, depending on the mass of the star, it could collapse into an incredibly dense object called a neutron star, essentially a city-sized atomic nucleus. If the star was truly colossal, the remnant could even be a black hole, a region of spacetime with gravity so strong that nothing, not even light, can escape. These remnants serve as nurseries for future stars and planets, continuing the cycle of cosmic creation and destruction. The formation of our solar system. Picture a colossal cloud, not of cotton candy, but of gas and dust, stretching across an unimaginable expanse of space. This wasn't just any cloud, it was the birthplace of our cosmic neighborhood, a swirling nebula of hydrogen, helium, and tiny specks of heavier elements, remnants of long-dead stars. Something disturbed this cosmic slumber, perhaps the shock wave from a nearby supernova, like a giant cosmic sneeze, causing the cloud to start collapsing under its own gravity. As it compressed, it began to spin, faster and faster, much like a figure skater pulling in their arms to spin quicker. This spinning motion flattened the cloud into a giant, rotating disk, a cosmic frisbee. At the heart of this spinning disk, gravity's relentless pull concentrated the majority of the material. This central mass grew hotter and denser, eventually igniting nuclear fusion, and voila, our sun was born. It was a fiery toddler, much more energetic and volatile than the star we know today. Meanwhile, the remaining gas and dust in the surrounding disk, like leftover crumbs on a cosmic plate, began to clump together. These weren't just random collisions, smaller bits stuck to larger bits, like dust bunnies under your bed, gradually growing into planetesimals, then protoplanets. Think of it as a cosmic game of snowball, where the snowballs just kept getting bigger and bigger. These protoplanets, still quite molten and chaotic, continued their gravitational dance, either merging with their neighbors or getting flung out into the cosmic void. Over millions of years, the debris cleared, and the orbits stabilized, leaving behind the planets we see today. The inner, hotter regions of the disk, closer to the Sun, were too warm for icy materials to condense, so rocky planets like Mercury, Venus, Earth, and Mars formed there, much like how only the sturdier toys survive a vigorous play session. Further out, where it was colder, the gas giants like Jupiter and Saturn, along with the ice giants Uranus and Neptune, could accumulate vast amounts of gas and ice, becoming the colossal behemoths of our solar system. It was a messy, violent, but ultimately creative process that shaped the diverse planetary family we inhabit. The birth of Earth. Our solar system, a cosmic neighborhood, began as a swirling cloud of gas and dust, a celestial nursery. This colossal cloud, probably triggered by a nearby supernova explosion, started to collapse under its own gravity. Think of it like a giant, slow-motion whirlpool forming in space. Most of this material gathered at the center, igniting into our sun. The rest, the leftover bits and pieces, flattened into a spinning disk, a bit like a cosmic pizza dough being tossed. Within this spinning disk, tiny dust grains began to stick together, like static electricity making your hair stand on end, but on a much grander scale. These clumps grew, attracting more material, becoming pebbles, then rocks, and eventually planetesimals, baby planets, if you will. Collisions were common, imagine a cosmic demolition derby happening constantly. Some impacts were gentle mergers, others were cataclysmic events that reshaped these nascent worlds. Our Earth was one of these planetesimals, and it grew by gobbling up its neighbors. It was a hot, molten ball for a long time, a fiery mess thanks to the energy from impacts and radioactive decay. This molten state was crucial because it allowed heavier elements, like iron and nickel, to sink to the core, while lighter elements floated to the surface. This process, called differentiation, is what gave Earth its distinct layers, a dense core, a rocky mantle, and a lighter crust. Then came a truly massive impact, a game-changer for Earth. A Mars-sized protoplanet, often nicknamed Theia, slammed into our young planet. This wasn't a fender bender, it was a world-altering collision. The impact was so powerful that it ejected a huge amount of material from both Earth and Theia into orbit. This debris eventually coalesced, forming our moon. It's like Earth got a giant cosmic souvenir, a constant reminder of its violent birth. The moon's formation also had a profound effect on Earth's rotation and stability, setting the stage for everything that was to come. The emergence of life. The universe, in its vast, cold expanse, wasn't always teeming with the vibrant chaos of life. For eons, it was a sterile, chemical soup. Then, on a tiny, watery world we now call Earth, something truly remarkable began to stir. It wasn't a sudden explosion, but a slow, almost shy, unfurling. Simple organic molecules, the building blocks of everything from bacteria to billionaires, started clumping together. Think of it like Lego bricks suddenly deciding they quite liked each other and forming little piles. These weren't alive, not yet, but they were getting ready. These early chemical concoctions, perhaps in the warm, mineral-rich waters near volcanic vents or even in shallow tide pools, found ways to self-replicate. Imagine a primitive photocopy machine, but instead of paper, it used simple chemicals, and instead of ink, it used, well, more chemicals. These replicators weren't perfect, sometimes they made mistakes, a bit like a photocopier smudging the page. But these mistakes were crucial. They led to variations, and variation is the raw material for evolution. Some replicators were better at gathering resources, some were more stable, and over time, the slightly better ones started to outnumber the less capable ones. It was a cosmic game of survival of the fittest, but on a microscopic scale, with no actual fitness trackers involved. Eventually, these self-replicating molecules wrapped themselves in a protective membrane, creating the first true cells. These were the original prokaryotes, the simplest forms of life, like single-celled bacteria. They were the ultimate minimalists, just a little bit of genetic code and a lot of attitude, surviving on whatever simple nutrients floated by. They were incredibly successful, spreading across the early Earth and essentially paving the way for everything that followed. They were the universe's first, tentative hello, world. A whisper that would eventually grow into a roar. These early cells then began to evolve, experimenting with different ways to get energy. Some learned to harness sunlight, a process we now call photosynthesis. This was a game changer, literally changing the atmosphere of the planet by producing oxygen. It's like the universe discovered solar power and decided to make a big, planet-sized advertisement for it. This oxygen, while essential for much of the life we know today, was actually toxic to many of the early life forms, forcing them to adapt or perish. The stage was set for more complex life, but it was a messy, trial-and-error process, a grand cosmic experiment where the failures were just as important as the successes. The evolution of life on Earth. The story of life on Earth is a wild ride, starting with tiny, single-celled organisms that were basically just little blobs of goo. Think of them as the primordial soup's first contestants in a very, very long reality show. These microscopic pioneers, appearing over 3.5 billion years ago, were the sole inhabitants of our planet for an astonishingly long time. They were the ultimate survivors, figuring out how to get energy from sunlight and chemicals, laying the groundwork for everything that came after. It wasn't exactly a bustling metropolis back then, more like a very quiet, very wet microscopic spa. Then, things started to get a bit more interesting. Around 2 billion years ago, some of these simple cells learned a neat trick. They started working together. This was the dawn of multicellular life, where cells began cooperating to form bigger, more complex organisms. Imagine a bunch of single-celled friends deciding to form a neighborhood watch, but instead of watching out for trouble, they were working together to, live. This cooperation led to the development of specialized cells, like the ones that would eventually become our skin or our muscles. It was a major upgrade from being a lone wolf in the primordial ooze. Fast forward a few 100 million years, and bam. The Cambrian explosion happened. This was like a biological fireworks display, where an incredible diversity of complex life forms suddenly appeared. We're talking about creatures with shells, legs, and even eyes. It was a period of rapid evolution, where nature seemed to be experimenting with all sorts of new designs. Think of it as Earth's first big makeover show, with new species popping up faster than you can say trilobite. This era gave us the ancestors of many of the major animal groups we see today, from fish to insects to early versions of things that would eventually crawl onto land. The journey wasn't always smooth sailing, though. Life on Earth has faced its fair share of do-overs, thanks to massive extinction events. These were like planet-sized reset buttons, wiping out a huge percentage of species. The most famous one, the one that took out the dinosaurs, was a real humdinger. But even after these catastrophes, life proved incredibly resilient. Survivors would then have a chance to fill the empty ecological niches, leading to new evolutionary pathways. It's like after a big storm, the remaining plants and animals get a chance to grow and adapt in new ways, sometimes leading to even more amazing forms of life. And that, in a nutshell, is how we got from simple blobs to, well, us. Still a work in progress, of course. The rise of intelligence. The universe, in its vastness, eventually gave birth to something truly remarkable: consciousness. It wasn't a sudden explosion, more like a slow bloom, a gradual unfolding of complexity. Think of it like baking a cake. You start with simple ingredients: flour, sugar, eggs, and through a process of mixing and heating, you get something far more intricate and delightful. Similarly, the basic elements forged in stars, after eons of swirling and clumping, eventually formed planets. On at least one of these rocky worlds, under the right conditions, life began to stir. Simple, single-celled organisms, like tiny, self-replicating blobs, were the first sparks of this nascent awareness. They were content with the basics, just surviving and multiplying. No existential crises for them. Over millions of years, these humble beginnings evolved. Life diversified, becoming more complex, more organized. Imagine a single-celled organism deciding, you know what? Sticking together might be more efficient. And thus, multicellular life was born. Then came specialization, where different cells took on different jobs, like a tiny biological factory. This led to the development of nerve cells, the universe's first attempt at a communication network. These early nervous systems were rudimentary, perhaps just enough to detect light or a chemical gradient. It was like the very first, clunky dial-up internet, but it was a start. The ability to react to the environment, to sense and respond, was a significant leap forward. The real game-changer, however, was the emergence of brains. These weren't just simple nerve nets anymore. They were centralized processing units, capable of storing information, learning, and making more sophisticated decisions. Think of the difference between a single-celled amoeba reacting to a food source and a dog figuring out how to open a door to get to its favorite treats. That's a massive jump in cognitive ability. This development allowed for more complex behaviors: hunting, avoiding predators, and even rudimentary social interactions. It's the universe's way of saying, okay, let's see what these things can do with a bit more processing power. And then, the ultimate upgrade: self-awareness. The ability to not just be but to know that you are. This is where things get really interesting, and frankly, a little weird. It's the moment when a creature can look at itself in a reflective surface and recognize its own image, or ponder its own existence. This level of intelligence allows for abstract thought, for the creation of tools, art, and language. It's the universe looking back at itself, trying to understand its own creation. It's a messy, beautiful, often hilarious process, filled with brilliant insights and spectacular blunders. We're still figuring it all out, you know. The future of stars. Stars, those celestial diamonds we admire, have a fascinating life cycle, and their future is a grand cosmic drama. Think of them like people: they are born, they live, and they eventually die, though on timescales that make our own lives seem like a blink of an eye. Our sun, for instance, is currently in its prime, burning hydrogen fuel like a well-functioning car. But one day, this fiery engine will sputter. In about 5 billion years, our sun will start to swell, becoming a red giant. It'll puff up so much that it will likely engulf Mercury and Venus, and maybe even Earth. Talk about a bad hair day for our planet. After this dramatic expansion, the sun will shed its outer layers, creating a beautiful, glowing cloud called a planetary nebula. What's left behind will be a tiny, dense core known as a white dwarf. This little cinder will slowly cool over trillions of years, eventually fading into a cold, dark ember, a cosmic ghost. The fate of stars, however, isn't a one-size-fits-all story. It depends heavily on their mass. Smaller stars, like red dwarfs, are much more frugal with their fuel. They burn incredibly slowly, and some scientists believe they could live for hundreds of trillions of years, far longer than the current age of the universe. Imagine a star so old it's seen galaxies form and die multiple times. These long-lived stars will eventually exhaust their hydrogen and slowly contract, becoming white dwarfs, much like our Sun's eventual fate, but over an unimaginably longer period. They won't go out with a bang, but rather a very, very, very slow fade. More massive stars, on the other hand, live fast and die hard. These stellar giants, much bigger than our Sun, burn through their fuel at an astonishing rate. When they run out of nuclear fuel, they don't just quietly fade away. Instead, they collapse under their own immense gravity and then explode in a spectacular event called a supernova. This explosion is so powerful that it can briefly outshine an entire galaxy. It's the universe's ultimate fireworks display, scattering heavy elements, like iron and gold, across space. These elements are crucial because they are the building blocks for new stars, planets, and even life itself. So, that gold ring on your finger. It might have originated in a star explosion billions of years ago. After a supernova, what's left depends on how massive the star was initially. If the star was moderately massive, the core that remains will be crushed into an incredibly dense object called a neutron star. These are so dense that a teaspoonful would weigh billions of tons, heavier than all the cars on Earth combined. If the star was exceptionally massive, its core will collapse even further, forming a black hole, a region of spacetime where gravity is so strong that nothing, not even light, can escape. These cosmic vacuum cleaners are mysterious and powerful, gobbling up anything that gets too close. The universe is a place of constant change, and the future of stars is a testament to this ongoing cosmic evolution, a cycle of birth, life, and spectacular, sometimes quiet, death. The fate of galaxies. Galaxies, those grand cosmic cities filled with billions of stars, aren't built to last forever in their current forms. Think of them like bustling metropolises. Over immense stretches of time, they'll undergo dramatic transformations, sometimes merging with their neighbors in a slow-motion celestial dance. Our own Milky Way is on a collision course with the Andromeda Galaxy, a cosmic rendezvous predicted to happen in about 4.5 billion years. It won't be a fiery crash, though. Galaxies are mostly empty space, so stars are unlikely to collide directly. Instead, their gravitational pull will stretch and distort each other, eventually merging into a single, larger galaxy. It's like two busy freeways merging. Traffic might get a bit chaotic for a while, but eventually, it all flows together. Some galaxies, particularly smaller ones, might get completely swallowed by larger neighbors. This process is called galactic cannibalism. Imagine a big shark gobbling up a smaller fish. The larger galaxy's gravity pulls in the stars, gas, and dark matter of the smaller one, integrating them into its own structure. This is a slow, drawn-out process, happening over billions of years, leaving behind only faint trails of stars that were once part of the consumed galaxy. These trails are like the lingering scent of a meal, a subtle reminder of what used to be. The ultimate fate of many galaxies is tied to the expansion of the universe itself. As the universe continues to expand, galaxies that are not gravitationally bound to each other will move further and further apart. Eventually, they will recede from view, becoming so distant that their light will no longer be able to reach us. It's like watching ships sail over the horizon. They get smaller and smaller until they disappear from sight, and eventually, you can't even see them with the most powerful telescope. This cosmic isolation means that in the far future, the night sky might look very different, with fewer visible galaxies. Even for galaxies destined to merge or be consumed, their internal structures will change. Star formation rates can be dramatically altered during mergers. A galactic collision can compress gas clouds, triggering bursts of new star birth, like a cosmic fireworks display. Other galaxies might enter a quiescent phase, where star formation significantly slows down or stops altogether, leaving them with mostly older stars. This is akin to a city's economy booming with new industries and then later settling into a more stable, mature phase with established businesses. The universe is a dynamic place, and galaxies are constantly evolving, their stories written in the language of gravity and light over eons. The expansion accelerates. It turns out, the universe's expansion isn't just chugging along at a steady pace. For a long time, scientists thought it was either slowing down, like a ball thrown in the air, or moving at a constant speed. But then, in the late 1990s, observations of distant supernovae, which are like cosmic lighthouses, revealed something quite astonishing: the expansion is actually speeding up. It's like discovering your car, which you thought was coasting downhill, is somehow flooring the gas pedal all on its own. This acceleration is a relatively recent phenomenon in cosmic history, but it's profoundly changing the universe's future. This cosmic speed-up is attributed to something called dark energy. We can't see it, we can't touch it, and we don't fully understand what it is, but its effects are undeniable. Think of it as an invisible force, spread throughout space, pushing everything apart. It's not like gravity, which pulls things together. Dark energy is the ultimate cosmic extrovert, constantly trying to create more personal space for every galaxy. This repulsive force seems to be getting stronger or becoming more dominant as the universe expands. The implications of this accelerating expansion are pretty mind-boggling. If this trend continues, galaxies that are currently visible to us will eventually recede so far and so fast that their light will no longer be able to reach us. Imagine a party where everyone is slowly drifting away from each other, and eventually, you can't even hear the music from the other side of the room. In the far, far future, the night sky might become a rather lonely place, with only our local group of galaxies remaining visible. It's a cosmic farewell tour, happening on a grand scale. This accelerating expansion also means that the ultimate fate of the universe is likely not a big crunch where everything collapses back in on itself, but rather a big freeze or big rip. A big freeze suggests the universe will just keep expanding and cooling until everything is so spread out and cold that no activity can occur. A big rip is even more dramatic, where the acceleration becomes so intense it could eventually tear apart galaxies, stars, planets, and even atoms themselves. It's a bit like an overinflated balloon that eventually pops, but on an unimaginably vast scale. Dark energy's enigma. Imagine the universe as a giant, expanding balloon. For a long time, scientists thought gravity, like the rubber of the balloon, would be slowing down this expansion. But then, a cosmic surprise. Observations showed the balloon isn't just expanding, it's speeding up. It's like someone is blowing harder and harder into the balloon, making it inflate faster and faster. This mysterious something pushing everything apart is what we call dark energy. It's not something we can see or touch, and it doesn't seem to interact with normal matter or light. It's the universe's ultimate ghost. Scientists estimate that dark energy makes up about 68% of the entire universe. That's a whopping majority. Think of it like this: if the universe were a pizza, dark energy would be most of the toppings, the crust, and maybe even the box. Normal matter, the stuff we can see and understand like stars, planets, and us, is only about 5%. The rest, about 27%, is dark matter, another invisible substance that pulls things together. So, we're basically living in a universe dominated by things we can't directly detect. It's a bit like trying to understand a party by only seeing the shadows of the guests. What could this dark energy be? One leading idea is that it's a property of space itself. As the universe expands, more space is created, and this new space comes with its own dark energy, causing even more expansion. It's a bit like a self-perpetuating cycle of outward push. Another possibility is that it's some kind of exotic energy field we haven't discovered yet, a bit like discovering a new fundamental force that's always been there, just too weak to notice until the universe got really big. The implications are mind-boggling. If dark energy continues to dominate, the universe might eventually expand so much that galaxies become isolated islands, too far apart to ever interact again. It's a lonely thought, but also a fascinating one. The enigma of dark energy is one of the biggest puzzles in modern physics. We know it's there because of its effect on the universe's expansion, but its true nature remains elusive. It's like finding footprints in the sand but having no idea who or what made them. Astronomers are working hard, using powerful telescopes and clever experiments, to try and shed more light on this cosmic mystery. Understanding dark energy could revolutionize our understanding of gravity, space, and the ultimate fate of the cosmos. It's a cosmic detective story, and we're still very much in the early chapters. The Big Rip Scenario. Imagine the universe as a giant, stretchy balloon. We know it's expanding, but what if that expansion starts to speed up, not just a little, but a lot? That's the core idea behind the Big Rip Scenario. It's a rather dramatic end of the world for everything, from the smallest atoms to the largest galaxies. Think of it like a cosmic tug-of-war where the force pulling everything apart eventually wins, and wins big. This cosmic stretching isn't just about galaxies drifting further from each other, it's about the very fabric of spacetime being ripped asunder. At first, galaxies would be torn apart. Then, stars and planets would follow suit. Eventually, even the atoms themselves, the tiny building blocks of everything we know, would be ripped open, their protons and neutrons no longer able to hold together. It's a rather messy end, unlike the slow fade of other theories. The key ingredient for this doomsday is something scientists call phantom energy. This isn't your everyday energy, it's a hypothetical form of energy that actually increases in density as the universe expands. So, the more the universe stretches, the stronger this phantom energy gets, fueling even more stretching. It's like a runaway train that picks up speed with every mile it travels, except this train is carrying the entire universe towards oblivion. If the Big Rip were to happen, it wouldn't be a sudden poof moment. It would be a progressive dismantling. First, the clusters of galaxies would break apart. Then, our own Milky Way galaxy would be ripped from its neighbors. Our solar system would be next, planets flying off in different directions. Finally, the Earth itself would disintegrate, followed by the Sun, and then everything down to the subatomic level. It's a chilling thought, but thankfully, current observations suggest this scenario is unlikely. The Big Crunch scenario. The universe might not expand forever. Instead, it could reach a point where gravity, the cosmic glue holding everything together, finally wins. This is the essence of the Big Crunch scenario. Imagine throwing a ball up in the air. If you don't throw it hard enough, gravity pulls it back down. In a similar cosmic fashion, if there's enough stuff in the universe, enough mass and energy, its collective gravity could halt the expansion and then reverse it. This reversal would mean galaxies would start hurtling towards each other, not drifting apart. The universe would begin to shrink. As it contracts, it would get hotter and denser. Think of squeezing a balloon, the air inside gets compressed and warmer. Stars would collide, black holes would merge, and eventually, all matter and energy would collapse into an infinitely dense point, much like the state from which the universe is thought to have begun. It's a dramatic cosmic rewind. So, what would this look like? Picture a movie playing in reverse, but on a scale that dwarfs any Hollywood production. The cosmic microwave background radiation, the faint afterglow of the Big Bang, would become intensely bright and hot. Distant galaxies, instead of appearing red-shifted, indicating they are moving away, would become blue-shifted, signaling their approach. It's a scenario where the universe effectively implodes. This ultimate fate, the Big Crunch, depends heavily on the universe's overall density. If the density is above a certain critical value, gravity will eventually overcome the outward push of expansion. However, current observations suggest the universe's expansion is actually accelerating, driven by something called dark energy. This makes the Big Crunch scenario less likely, but not entirely impossible. Science is always on the lookout for new clues. The Big Freeze scenario. The universe's ultimate fate might be a slow, cold fade into nothingness, a scenario cosmologists call the Big Freeze. Imagine the universe as a giant, ever-expanding party. For a while, there's plenty of energy, lots of dancing, stars shining, galaxies colliding, and things are hot and exciting. But as the party goes on, the energy gets spread thinner and thinner. The music starts to fade, the lights dim, and eventually, everyone gets tired and goes home. This spreading thinner is due to dark energy, a mysterious force that's pushing everything apart, making the universe's expansion accelerate. Think of it like a balloon with dots on it. As you inflate the balloon, the dots move further apart. Dark energy is like an invisible hand continuously inflating that balloon, making the expansion speed up over time. So, galaxies that are already far away will move away from us even faster, eventually becoming so distant that their light will never reach us again. It's like trying to have a conversation with someone on the other side of a stadium that's constantly getting bigger. Eventually, all the stars will burn out. Our sun, for instance, will become a white dwarf, then a black dwarf, a cold, dark ember. Galaxies will become collections of dead stars, black holes, and rogue planets drifting in an increasingly vast and empty space. Even black holes, those cosmic vacuum cleaners, aren't eternal. Through a process called Hawking radiation, they will slowly evaporate over unfathomable timescales. It's like leaving a pot of water on the stove forever. Eventually, all the water will evaporate, leaving nothing behind. The universe will become a frigid, dark, and incredibly dilute place. The temperature will approach absolute zero, the coldest possible temperature. There will be no more heat, no more light, no more activity. It's the ultimate cosmic lights out. While this might sound a bit bleak, it's a fascinating concept that highlights the immense timescales and fundamental forces shaping our universe. It's the universe's final yawn before a very, very long sleep. The multiverse hypothesis. The idea that our universe might be just one among countless others is a mind-bending concept known as the multiverse hypothesis. Think of it like a cosmic bubble bath, where each bubble is a complete, self-contained universe, and ours is just one of them. Some scientists suggest that these other universes could have different physical laws, making them vastly different from our own. Imagine a universe where gravity pushes things apart instead of pulling them together, or where the speed of light is as slow as a car on a highway. It's a wild thought experiment that arises from trying to explain some of the peculiar aspects of our own universe. One of the ways this hypothesis pops up is through the theory of cosmic inflation. This is the idea that the universe expanded incredibly rapidly in the moments after the Big Bang. Some models of inflation suggest that this process might not have stopped everywhere at once. Instead, it could be an ongoing phenomenon, constantly spawning new, bubble universes from a larger, eternally inflating parent space. So, while our universe finished inflating and settled down, other regions might still be busy inflating and creating more universes, like a cosmic bakery constantly churning out new loaves. Another avenue leading to the multiverse idea comes from quantum mechanics, the quirky science of the very small. One interpretation, the many worlds interpretation, suggests that every time a quantum event has multiple possible outcomes, the universe splits. In one universe, outcome A happens, in another, outcome B occurs. This would mean that for every decision you've ever made, there's another you in a different universe who made the opposite choice. Did you choose coffee this morning? Well, in another universe, you're sipping tea right now, and that universe branched off from ours at that precise moment. It's a bit like a choose-your-own-adventure story on an unimaginably grand scale. While these ideas are fascinating, it's important to remember that the multiverse hypothesis remains a theoretical framework. We don't have direct observational evidence to prove or disprove the existence of other universes. They are, by their very nature, incredibly difficult, if not impossible, to detect. However, these concepts are not just idle speculation, they emerge from our best scientific theories about the universe's origins and workings. They provide potential explanations for why our universe appears so finely tuned for life, suggesting that if there are infinite universes, it's not so surprising that at least one of them, ours, would happen to have the right conditions for us to exist and ponder such things. The search for extraterrestrial life. The vastness of the cosmos has always sparked our curiosity about whether we are alone. This fundamental question fuels the search for extraterrestrial life, a scientific endeavor that spans radio telescopes, space probes, and the analysis of exoplanet atmospheres. Scientists are looking for biosignatures, which are like alien fingerprints, indicators that life might exist or have existed elsewhere. These could be gases in an atmosphere that are produced by living organisms, similar to how plants on Earth produce oxygen. One of the primary methods involves listening to the cosmos. The search for extraterrestrial intelligence, SETI, uses giant radio dishes to scan the sky for artificial signals, deliberate messages or even accidental leaks from alien civilizations. Think of it as trying to pick up a faint radio broadcast from a distant city, but on a cosmic scale. So far, no definitive alien radio waves have been detected, but the search continues, covering more and more of the sky and listening at different frequencies. It's a bit like searching for a specific needle in an infinite haystack, but the potential reward is immense. Beyond just listening, we're also looking for the building blocks of life. Missions to Mars, like the Perseverance rover, are searching for signs of past microbial life in ancient lake beds. They analyze rocks and soil, looking for organic molecules, the carbon-based compounds that form the basis of all life as we know it. While finding these molecules doesn't automatically mean we've found aliens, it tells us that the ingredients for life are present, which is a crucial first step. It's like finding flour and sugar in an abandoned kitchen. It suggests that baking might have happened, even if the baker is long gone. Furthermore, the discovery of thousands of exoplanets, planets orbiting stars other than our Sun, has revolutionized the search. Telescopes like the James Webb Space Telescope can now analyze the atmospheres of some of these distant worlds. By studying the light that passes through an exoplanet's atmosphere, scientists can identify its chemical composition. If they detect a combination of gases that is unlikely to occur naturally, such as oxygen and methane together in significant amounts, it could be a strong hint of biological activity. It's a bit like smelling smoke and knowing there's a fire, even if you can't see the flames directly. This indirect evidence is a powerful tool in our ongoing quest to answer that age-old question, are we alone? The cosmic horizon. The universe is a vast place, and we can only see so far. This limit to our vision is called the cosmic horizon. Think of it like standing on a vast, flat plane. You can only see so far before the curvature of the Earth hides things from view. In the universe, it's not the Earth's curve, but the finite speed of light and the age of the universe that create our horizon. Light from the most distant objects has been traveling towards us since the beginning of the universe. However, because the universe has a history, there are regions so far away that their light simply hasn't had enough time to reach us yet. It's like trying to hear a whisper from across a football field. The sound waves just can't make it in time. This means that what we observe is a snapshot of the universe as it was billions of years ago, not as it is right now in its entirety. The observable universe, the part we can theoretically see, is a sphere centered on us. The edge of this sphere is our cosmic horizon. If we were in a different galaxy, our cosmic horizon would be centered on that galaxy, and we'd see a slightly different set of stars and galaxies. It's a bit like having a personal bubble of visibility, but this bubble is defined by the fundamental laws of physics and the age of everything. This cosmic horizon isn't a solid wall, it's more of a conceptual boundary. Objects beyond this horizon exist, but their light is still on its way. As time goes on, light from more distant regions will eventually reach us, and our observable universe will expand. However, due to the accelerating expansion of the universe, there are also regions that are moving away from us so fast that their light will never reach us, effectively receding beyond our future horizon. It's a bit like watching a balloon inflate. Things on the surface get further apart, and some might even drift out of sight permanently. The ultimate fate of information. The universe's grand finale, whatever form it takes, holds a profound implication for information. Think of information as the unique arrangement of things, like the specific sequence of letters that make up your name, or the precise pattern of pixels on your screen. Even in the most extreme cosmic scenarios, the fundamental question remains, does this information endure, or is it irrevocably erased? One leading theory suggests that the universe might end in a big freeze, where everything cools down to absolute zero. In this chilling scenario, all activity would cease. Atoms would stop vibrating, stars would fade, and even black holes would eventually evaporate through Hawking radiation. It's like a computer that's been unplugged and left in a dark, cold room. Its programs and data are still technically there, but inaccessible, like a forgotten hard drive in a dusty attic. Another possibility is the Big Rip, where the expansion of the universe accelerates so violently that it tears apart galaxies, stars, planets, and eventually, even atoms themselves. Imagine a balloon being inflated so rapidly that it pops, scattering its fragments everywhere. In such a chaotic end, the intricate structures that encode information would be obliterated. The specific arrangement of particles, the very essence of what makes a thing unique, would be lost in the cosmic shrapnel. Then there's the Big Crunch, a reversal of the Big Bang where the universe collapses back on itself. This could potentially reset everything, erasing all prior information and setting the stage for a new cosmic cycle. It's akin to hitting the factory reset button on a phone, wiping all your apps and contacts clean. However, some physicists ponder whether even in such a reset, a faint echo of the previous universe's information might somehow persist, like a ghost in the machine. The ultimate fate of information is a deeply philosophical question intertwined with the universe's physical destiny. The end of everything, or just the beginning? The universe's ultimate fate is a cosmic question mark, a grand finale that could be either a silent fade-out or a spectacular rebirth. Scientists ponder scenarios where the universe might simply keep expanding forever, a process called the Big Freeze. Imagine a giant balloon being inflated, but instead of popping, it just gets bigger and bigger, with galaxies drifting further apart until they are mere specks in an ever-darkening void. Eventually, even stars will burn out, and black holes will evaporate through Hawking radiation, leaving behind a cold, empty expanse. It's like the ultimate power down, a universe that slowly but surely runs out of steam. Another possibility is the Big Crunch. This is the opposite of the Big Bang, where gravity, instead of being overcome by expansion, eventually wins. The universe would stop expanding and start contracting, galaxies rushing back towards each other like a cosmic rewind button. Picture all the pieces of a shattered vase flying back together to form the original object. If this happens, the universe might collapse into an infinitely dense point, a singularity, potentially triggering another Big Bang and a new universe. It's a cosmic reset, a cyclical existence where endings are just preludes to new beginnings. Then there's the Big Rip, a more violent conclusion. In this scenario, dark energy, the mysterious force pushing the universe apart, becomes so powerful that it overcomes all other forces, including gravity, and even the forces holding atoms together. Galaxies would be torn apart, then stars, planets, and eventually, matter itself would be ripped asunder. It's like a cosmic shredder, reducing everything to its most fundamental, unbound particles. A dramatic end, to say the least. Ultimately, whether the universe ends in a quiet whimper or a bang that sparks a new creation depends on the nature of dark energy and the precise balance of forces at play. For now, we are living in a universe that seems to be accelerating its expansion, leaning towards the big freeze or perhaps the big rip. But the beauty of science is that our understanding is constantly evolving, and the final chapter of the cosmic story is still unwritten, leaving room for surprises and, perhaps, a grand, unexpected beginning. And so, from a tiny, fiery spark to the vast, star-dusted expanse we see today, the universe has undergone an incredible journey. We've witnessed the birth of stars, the dance of galaxies, and the emergence of life on at least one small, blue planet. It's a cosmic story that continues to unfold, a breathtaking epic playing out across billions of years and countless light years. What do you think is the most amazing part of this cosmic evolution? Let us know in the comments below. And if you're as fascinated by the universe's grand narrative as we are, then you won't want to miss our next episode, where we'll explore the mind-bending concept of dark matter, the invisible scaffolding that holds galaxies together.